Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. The topic was binary tree and the pattern was lowest common ancestor. So as we have already learned about binary search tree, so let's move on to that question related to this, which is LCA of binary search tree. So let's read the problem statement. It says we will be given the binary search tree and we have to find the lowest common ancestor node of two given nodes. Okay, so basically as you can see the example number 1, it says we will be given the root of the binary tree, means the whole binary tree, and P and Q as two nodes, and our task is to check their lowest common ancestor. So I hope you would have watched the previous video which was about lowest common ancestor of two nodes in binary tree, but as this is binary search tree, so basically it will help us to decide which side to move, which will eventually decrease our time complexity. So let's read the constraint. Constraint says the minimum number of nodes will be 2, obviously that will be P and Q, and the maximum number of nodes can go till 10 power 5. Okay, so as the maximum number of nodes are 10 power 5, so we have to check or look for linear solution, because or n log n also we can go up to, means we have to close this under 10 power 8, because I hope you know that beyond 10 power 8 it might give us TLE, and for sure at 10 power 9 and 10 power 10 so it will give us TLE, because we have learned about time and space complexity earlier. I'll attach the video link here. So if 10 power 5, the maximum n can go till 10 power 5, so basically we have to close and solve this problem in linear or less than that if possible. Okay. Now the number of node value can also go from minus 10 power 9 to 10 power 9. So as we do not need to do the summation of two values, so hence it's not about summation or multiplication, so we don't have to play with the value. Means 10 power 9 is the maximum integer limit which an integer can hold, so we do not need to worry about the long conversion. Okay, so here is the P and Q which has been given. P is 2 and Q is 8. So if you see about the nearest common parent, common ancestor to both of these nodes are 6. So in the previous problem, which was about lowest common ancestor in binary tree, we were not aware which side we have to move, left side or right side. But as this is a binary search tree, means we know that in binary search tree, the root will be greater than the left subtree values, all values, and it will be smaller than all right subtree values. Correct? So it is 2 and 8, right? So let's think about what if our nodes will be 0 and 4, means P is 0 and Q is 4. So to 6 we can simply ask ki hey 6, out of this what is maximum? 4 is maximum. So if my 6 is greater than the maximum of P and Q, which is 4, so for sure I can say ki both of these P and Q lies in my left subtree. So we can ignore visiting my right subtree. Can I say that? Yes. Now we'll move on to 2. We are at 2. Now, what was the node? 0 and 4. So we'll see ki hey, is my 2 is greater than maximum, which is 4? No. It means 4 does not lie towards the left side. Okay. Now, is my 2 is smaller than 0 also? Why I am saying this? Because suppose for 7 and 9, 6 will be smaller than the smallest of P and Q also, na? So if my between 7 and 9, what is the smaller? 7. So if my node is smaller than the minimum of P and Q also, it means both the number lies towards my right side. Okay, so in 0 and 4 case we were at 2, so 2 is saying no, I am not greater than 4. Okay, means 4 lies towards right side, and also 2 is saying no, I am not smaller than 0. It means 0 lies towards left side. So means when neither of the cases are true, so we can say that one node lies towards my left side and one node lies towards my right side, and that is the case, right? So in that case we have to return the root instead of traversing below the levels. Okay, so let's write simply whatever we just discussed. So what was that? If my root dot value which is 6, so if this is greater than or equal to what? P. Similarly, if root dot val is greater than equal to Q, what does it mean? We could have also written if my root dot value is greater than math dot max of P and Q. Both will be true. Okay. So if my root dot value is greater than P, in this case, what is P? 2. No, it's not. Okay. But suppose if it was 0 and 4, so we can say ki root dot value 6 is greater than P? Yes. Root dot value 6 is greater than Q also 4? Yes. So it means the number or the node which we are looking for lies towards my right subtree. So whatever was the function, let's say like whatever was the function, so we have to basically return whatever that returns, what left side node. We have to call the same function again, and now we have to send root dot left instead of root and P and Q as it is. Okay. So here we would have root, we would have P and we would have Q. Okay. So this is my root. Now if my root dot like value is greater than both P and Q, which is 0 and 4, let's say. So in that case, we can say ki yes, our LCA would lie towards my left side. So whatever this function returns, return to the main call. Okay. Now we'll go for this. So now 2 is my root. So again we'll go here and check, is my root value 2 is greater than P, which is 0? Yes. And is greater than Q also? No. It means one to lies towards my left side, but the other node lies towards my right side, and hence I will be that lowest common parent. Correct? So we'll say else if. Else if why? Because what if it was 7 and 9? So in that case, so P like root dot value will be smaller than P and smaller than Q. So in that case, we have to go towards the right side also. Na? We can return root as the LCA only when one node lies towards my left side and one node lies towards my right side. Okay. So else if my root dot value, let's say when P is 7 and Q is 9. So if my root dot value is less than equal to P and root dot value is less than equal to Q, then we can say ki our answer, which is LCA, lies towards the right side. So just call for root dot right, correct, P and Q. That's it. And in the else case, when the else case will run, so basically this if case will run when both P and Q lies towards my left side. This else if case will run when both my P and Q lies towards my right side in the case of 7 and 9, right? But this else case will run when, like in this case, 2 and 8. So we will say ki is my P, which is 6, greater than 2? Yes. Greater than 8? No. It means 2 to lies towards my left side, but 8 does not lie. Correct? Similarly, is my 6 less than 2? No. It means 2 lies towards left side. And is my 6 less than 8? Yes. But they are lying towards both side, you can say. So in that case, the root itself will be the parent. So hence in the else case, we'll simply return root as our answer. And that's it. So let's do the dry run here. Okay. So obviously as this is a DFS call, so a stack would have saving all the function calls, right? So initially for function 6, let's say 2 and 8. For 2 and 8, we are trying to find the LCA. Now, for functions at 6 only, we will get to know, if this if case also not passing and this else if case also not passing, so hence we will return root. So from here and only, we'll get 6. Now, let's say instead of 2 and 8, we have 7 and 9, okay, as P and Q. So what will happen? From 6, we'll say this if case will not pass, but this else if case pass. Why? Because root is lesser than 7 and lesser than 9. So hence we have to go towards the right side, correct? So we'll call that second next function towards right, which is for 8, and 7, 9 will be the PQ. Again at 8 we'll check is 8 is greater than 7 and 9? No. Is 8 is less than 7, 9? No. It means we'll fall in this else case because one node lies towards my left side, one node lies towards my right side. So hence we'll return what? 8 as an answer. So from here we'll return 8. And as this was the call at right side, this was the call, right? So root will get returned here, and this return function will actually return back to the main function, which was 8. Okay. So if you see the time complexity here, we are actually we have called for 6. Okay. Now in the next level, we have not called for both the nodes. We went to only for one node, which was 8. Okay. If there were more such subnodes now, so we would have went on to the next node, but from every level, we would have chosen only one node. So hence the time complexity will be number of levels, which is log of n if it is a balanced tree. Okay. If it is a skewed tree, means it will be BST like 1, 2, 3, 4 and so on. So this is not balanced, this is skewed tree. So number of levels is nothing but number of nodes. So hence in that case the time complexity will be O of n. But if it is a balanced binary search tree, then it will be logarithmic of n. Okay. But because we are solving this using the recursive call, so by default obviously all the calls will get saved in the stack, and which will also make the space complexity logarithmic of n. Why? Because from every level, for whatever nodes you are making the call, that many number of calls it's saving in the stack, and that is making extra O of logarithmic of n space complexity, correct? If it is a balanced search tree. But if it is a skewed, then for sure we would end up saving all the calls for every nodes, correct? Yes, and hence space complexity will also go to O of n. But what if the interviewer asks you ki no, go for the space optimization? Means time is okay for O of n or O of log n based on skewed or balanced binary search tree, but space we have to optimize. And whenever the interviewer asks ki we have to optimize the space in constant, then for sure forget about the recursive function call. And in that case, start iterating from the root itself and just keep moving your root in simple while loop. That is nothing but called iterative approach. So if you understood this, iterative approach is also very easy. The only thing is, instead of this function call, we have to close it in a while loop until our root becomes null. And that's it. So let's write the code in the editor. So here's our editor. Let's write the code here. First, because it is iterative approach, so we have to close this in a while loop. While our root is not is equal to null, we have to keep iterating. What will be the iteration? If my root dot value is less than p dot value. Why? Because p is a node now, okay? And similarly, root dot value is less than q dot value. It means both my p and q lies towards my right side, so I have to move my root towards my root dot right side. Similarly, I have to close this in a next else if case, and here now the sign will be greater than. If my root is greater than both p and q, it means they lies towards left side. And now in the last else case, we have to simply return our root because that will be our answer. And after coming outside, we have to return null because the return type is tree node, okay? Now, why we have not put equal to sign here? Because the constraint says that all node values will be unique, okay? If it was supposed to be duplicate, we would have inserted. That's it. Now let's run the code and let's submit this. By the way, as this is an iterative approach, so definitely the space complexity will also be constant, okay? Because we are not using any extra space. If we would have done this using the recursive approach, then the space complexity will be O of n, number of levels basically, okay? Log n if it is balanced binary search tree. I hope you understood. So this was the code in Java. Here is the code in C++ with a similar approach, and here is the code in Python with a similar approach. So I hope you understood. If yes, then definitely you are eligible to go in the sheet and mark the next question asked. And that's it, guys. If you understood and really like the way of explanation, please do hit the like button because it gives me more motivation to make more videos for you all. And that's it. I'll attach the sheet link and my social media links in the description. You can also share your progress on social media by tagging Rising Brain or my page. That's it. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.